All right. Okay, so I'm a little disappointed in the lack of attendance in this class. But I hope they all watch the video. I want to tell you that we are having a quiz next class, which probably you know. So there's a quiz, which I don't know how to spell, Thursday. And as usual, it'll be in the last 45 minutes. And I want to tell you that it's one of the things it's on is limiting reactants, because this was the topic in chapter 4, the first part that we didn't get to for the exam. So definitely this is going to be on it. And I'm not sure. And also the lecture that I gave on limiting reactants didn't take. So there is no video to watch to catch up on that. Yeah. So, so you really need to go over the problems. If I have time today, I will go over a couple of them, but I might not have time. We'll see. So anyway, limiting reactants is one thing on there. Also, the reactions from Tuesday, you know, we had the precipitation, we had the acid plus carb, bicarb, and acid-base neutralization. You need to be able to write the products and, of course, balance and everything, and know what type of reaction it is. The reactions we're doing today are not on the quiz, so you don't have to worry about that. There was also some intro information on part 2 of chapter 4, which this is the handout I gave on chapter 4, part 2, and there's a lot of stuff at the beginning that you have to read, and about solubility and about precipitation and electrolytes and what is an acid and stuff like that. So that stuff you might see on the quiz as well. That intro information on part 2, which was on acids, what are bases, solubility, how to use the solubility chart. Do all ionic compounds dissolve? No. Remember, we looked at a thing that showed that you could have solid, liquid, or gas. Some solids dissolve, some liquids dissolve, some don't. I mean, there's just no pattern to figure out if a solubility of ionic compounds, which is why we give you the solubility chart. As for molecular compounds, it's very difficult to tell unless you learn about what's involved, which we do in Chem 104. So you're not responsible for that, but you should know that you can't really predict it. That's really the only thing you could know at this point, except, of course, using the solubility chart, which, of course, you have to know how to do for precipitation reactions. And for all of these reactions, you need to know how to write the correct formulas. And you need to realize that those correct formulas have nothing to do, like if you have a Na2CO3 on the left side of the equation, let's say, and you have NaCl on this side of the equation, this 2 does not tell you anything about what this formula is. You know, you have to balance by putting coefficients, but you never change the subscript of a correct formula. The formula is only one correct formula for an ionic compound, and it's the one that balances the charge, and that is that. Okay, so you know, don't get fooled by that. Let's see. All right, so that's really all I have to say about the quiz. I'm hoping to have a little extra time at the end of class today to go over some limiting reactant stuff, but we'll see how it goes. I have a very, very important type of reaction to tell you about today. It's a very different kind of reaction. And I'd like to show you something about it. So what we're going to be doing is oxidation-reduction. God, I can't get it out of my head that it's OX, not Q. Oxidation-reduction reactions, otherwise known as redox, for obvious reasons. So I want to show you one of these reactions. Well, first of all, the first reaction I'm going to show you is not an oxidation reduction. So up until now, here's a typical reaction that we've looked at. This is not redox. And this reaction should be familiar to you. Well, the type of reaction. I'm going to ask you, what is the type of reaction that this is? What will the products be in this reaction? What's one of the products? Double exchange, right? This cation, this anion. What do you get? AgCl solid plus NaNO3. Okay, sodium nitrate is soluble, so I put an aqueous there. AgCl, if you look on the solubility chart, is a solid. It's not soluble. So this is a precipitate. So this is a precipitation reaction. But what I want to do is examine the players in this reaction very carefully. The players are the reactants and the products, but even more specifically, I want to look at the individual ions that are present here. So on the left side, we have silver. What is the form of silver on the left side of the equation? AgNO3 is what type of compound? Ionic. So Ag is actually the silver ion, right? These are 1+ ions, right? If you look on this side of the reaction, what is the form of silver? It's not a trick question, really, but it might seem it. It's also Ag+, but it's in a solid AgCl precipitate, but it's still silver ions. Okay, if we look at sodium, on this side, we have a sodium ion floating around in solution. Sodium on this side is still sodium ion. This seems rather stupid, right? But I'll show you why it's not in a minute. Chlorine is in the form of Cl- on both sides. Okay, and nitrate also is the same on both sides. So what's going on here is that all of the participants in this reaction have the same charges. Nothing changed about the charge on silver. So all the charges of all the participants in this reaction stay the same. Okay? So nothing has changed about the distribution of electrons. The distribution of electrons is absolutely the same. So now I'm going to show you an oxidation-reduction reaction, which is one of the ones that you need to learn. So this is your first redox reaction. And it's called metal plus salt. That's what I call it. And zinc reacts with copper chloride, which is in solution, to form zinc chloride and solid copper. So now, if you look at this equation, you see it's not quite the same. Oh, by the way, what's happening here is that zinc displaces the copper. It kicks the copper out, it replaces it, and you end up with solid copper here, whereas you had a copper ion here. So let's look at the different sides of this reaction and see what we can see. Okay, so let's look at zinc. On the left side, what do we have? We have zinc metal. This thing is not charged. This has a charge of 0. It's neutral. All these things kind of mean the same thing. It's solid, and it's on the bottom of the flask. Right, and over here, we have zinc 2+ ions. Okay, it's part of zinc chloride, even though it's really floating around in solution. Let's not put that in because it's really floating around. What does it mean when I say floating in solution? What I mean is that it's aqueous because it's soluble. Zinc chloride is a soluble ionic compound. So it's a dissolved ion. You can't see it, it's clear. So over here, you have a solid on the bottom of the flask. It's a shiny solid. Here you have a clear solution, which is for the zinc. Okay, so what's happened is it's changed now. It's a cation. It has a 2+ charge. Over here again on the left, we had copper, and copper chloride is in the form of copper 2+. This is a cation. It's a dissolved ion. It actually makes the solution blue. Very light blue. Okay, a sort of blue-green. It's a dissolved ion, as I said, right? But over here, copper is solid copper. It's sitting on the bottom of the flask. Well, it's probably fine particles, so it's probably not on the bottom of the flask, but it is solid copper. It has a charge of 0, so we say it's neutral. Okay, as for the chloride, it's the same on both sides. That hasn't changed. It's chloride ions here, it's chloride ions here. So there's nothing big going on there with the chlorine. Okay, but something else big has really happened here. And what that something else is that happened is there has been a change, a fundamental shifting of charges, a fundamental shifting of electrons. Copper 2+ went to copper with no charge, okay? And zinc with no charge went to zinc 2+. Okay, so there's been, so what happened here was that zinc loses 2 electrons and copper gained those electrons, those 2 electrons. So basically electrons were transferred from zinc to copper ions. It didn't start out as copper neutral, it started out as Cu2+, so that's where the electrons went to. So in fact, I can write those 2 things out a little more completely. I can write, zinc loses 2 electrons, so zinc goes to zinc 2+ plus 2 electrons. So it lost those 2 electrons, and there they are. And then copper gained those electrons. So essentially 2 electrons are transferred from zinc to the copper ion. So reactions that shift electrons like this, and this is what most reactions are. Many reactions are redox reactions where electrons are shifted around. So reactions like this that shift electrons around are oxidation-reduction reactions, which we call redox for short, or redox reactions. One chemical species, that's what I call something, like a copper ion is a chemical species. Copper is a chemical species. I know it sounds very strange, but chemists use this terminology just to refer to any different, chemical you might see in the equation, okay? So one chemical species gains electrons, one chemical species loses electrons. So oxidation is loss of electrons. Yeah, rust is an oxidation reduction reaction, yes, because iron loses electrons and oxygen gains those electrons. Reduction is gain of electrons. These go hand in hand. You cannot have one without the other. Something has to provide the electrons that are lost, and something else picks them up. So both have to happen. You can't just have one happening. There's a way of memorizing this that people like. Oxidation is losing. Reduction is gaining electrons, okay? Another one that we used to use a lot was Leo says grr. Does that even, do you know, Leo is the lion, right? Leo the lion, whatever. Lose electrons oxidation, gain electrons reduction. Okay, so now you might ask the question, somebody muttered, gain of electrons is reduction? Like, what the heck is that about? So do they call it reduction just to confuse students and make them say, oh, it's the opposite of what I think, you know? No, the reason why gaining electrons is reduction is because when electrons are gained, it reduces the charge, right? So gaining electrons reduces the charge on a chemical. Let me just say on an element. Because we're talking, usually it's just, it can be one element within a compound. Let's just call it element, okay? So for example, copper, 2+, leave a space, goes to copper, okay? And it does this by gaining 2 electrons. So copper started out with a +2 charge here. It ended up with a 0 charge. So the charge on copper is reduced. Went from +2 to 0 as it gained 2 electrons. Okay, now we call this number the charge associated with an element or an ion. We call it the oxidation number. So this number is the oxidation number. The oxidation number, yes. And for ions and for pure elements like copper, it's easy to tell what the oxidation number is. Later on, I will help you learn, I hope, how to assign oxidation numbers for molecular compounds, which is more difficult. Okay, so we call this an oxidation number. You'll hear that a lot today. Okay, so let's go and look again at this original reaction. And I want to sort of break it down to the basics. Solid zinc plus aqueous copper chloride goes to zinc chloride plus copper. Oh, by the way, this I call metal plus salt. This is a metal. This is a salt. Okay, but it's sometimes also referred to as a single replacement reaction, where the zinc replaces the copper. Okay, it's also often called single displacement or displacement. You will see these types of names for this type of reaction. But what I want you to notice here is what's really happening here. Okay, so this copper chloride here is aqueous, all right? Oops. So that means that you really have here copper ions and 2 chloride ions for each of those formula units. And over here, This shouldn't say solid here. How come you're not getting your gotcha points out there, you know? This is a solid here, okay? This is aqueous as well. So this is zinc ions and chloride ions. So I have these two chlorides here on both sides of the equation, okay? And what I can do is I can, since they're not really involved, I could kind of cancel them out. So I could write this as zinc solid plus copper ion plus 2 chloride ion, because that's what this is, goes to zinc ion and 2 chloride ions plus copper. This is actually doing the net ionic equation, which is not something I'll require you to be able to do, but I just want you to see that when you do this, what you end up with is sort of the essence of this reaction. Okay, so now you can really see, you don't have the chlorides there messing up the picture, clouding it up and making it hard to see what's going on. Now you can really see that you kind of have these two half reactions going on, which I actually wrote before, but I'll write them again. You have zinc solid going to zinc 2 plus 2 electrons. So it lost those electrons. Then you have copper in the form of copper ions, aqueous copper ions, picking up those 2 electrons and forming copper solid. Okay. In fact, if you add these two up, you exactly get this one here. This is the sum of these two things, because the electrons would cancel.
So on the left is the way to know that zinc has no charge because it's solid.
Yes.
Okay, so if we look at the
No, or if you just saw Zn, you would know that that's pure zinc. You would be able, if you saw that, you would know it's solid and you know it has a 0 oxidation number.
would it go by the periodic?
No. No, any metal, any, if I write sulfur, that's 0. Or O2, those O's are 0. Well, that's for later, okay? For now, we have these two half reactions. And what I can do is I can write what we call the oxidation numbers on top. Okay, so zinc is neutral, has no charge. Here it's +2. So zinc is being reduced, oxidized to zinc ion, Zn2 plus ions. Here I have a +2 on the copper. So copper 2 plus is reduced. Yes, is reduced to copper solid. Okay, a charge goes from +2 to 0. It's reduced. This one is going up, it's oxidized. Okay. All right. So the reaction here occurs readily in a test tube. Let me just rewrite that reaction again because I have to scroll down. But I'm going to now write it again, but I'm doing it for a reason. Okay, so I want to consider this reaction and then a very similar one. Let me just write in the phase here. Okay. So this reaction occurs very readily. So what I mean by that is if I take some zinc and I plunk it into copper chloride, right away you'll see some solid copper particles being formed, and you will see the blue-green color of this eventually disappear. So this reaction happens right away on its own. I mean, okay, now I want to show you another reaction that's very similar. So let's consider this reaction. So consider this one. This closely related, I'll say. Okay, copper solid plus zinc chloride goes to copper chloride plus zinc solid. So would this reaction occur if I took copper so I have a solution of zinc chloride and I plunk a penny into it, or a piece of shiny copper. Maybe a penny is too oxidized to react very well, but a nice shiny copper, plunk it in. You would notice that this reaction does not happen. So you might ask the question, why? Why is zinc able to replace copper, but copper cannot replace zinc? That will not happen. Okay, and the reason for that is that metals are not all alike, okay? Metals, some of them are more active than others. Some are more reactive than others. So but the way of just generalizing that is saying metals are not all the same reactivity. Zinc is more easily oxidized, because here, this is an oxidized form of zinc. This is +2 here. This is a reduced form, 0. Zinc is more easily oxidized than copper. Another way of saying that is it is more comfortable with a positive charge. It is a more, what we say, active metal. So metals do not all have the same activity. So the reason why is that metals are not all alike. Some are more active, which really means reactive, than others. Zinc is more easily oxidized than copper. So what happens is that zinc will replace copper in this type of reaction and become positively charged. Can you just wait for me to finish this thought? Zinc will replace copper in this reaction and become positively charged, become a positively charged ion. But copper can't do this to zinc. Way of saying that zinc more readily accommodates, I don't know how else to say it, a positive charge. So it's more easy to get a positively charged zinc than copper. Yeah, what's you saying?
So like the activity.
I don't think it's that easy to tell. But you have Dr. Longfellow. Well, he might know the answer to that because he specializes in organic chemistry, and I don't. So he would have a better answer to that than I do. Okay. So more active metals basically replace the less active ones in this type of reaction.
Are we gonna have this sheet, for example,
What is that sheet?
the oxidation states?
No, I didn't pass that out. Oh, wait, what sheet?
The oxidation states of the.
Why did I pass that out? No. I think this out. Dr. Wondershee.
Maybe it's got some.
I'll give you the oxidation number rules, but I won't give you that. All right. So more active metals replace less active ones. And so the more active metal gets oxidized, the less active metal gets reduced. So in this reaction, the more active metal, which is zinc, gets oxidized to zinc ion. The less active metal, copper, in the form of copper ion, gets reduced and to copper. Okay, so how do you know if something is a more active metal or not? That I can help you with. Okay, so let's see, metal activity chart. So this is metal activities are known extremely well. And so this is just a little bit of what we know. This thing, if you take your packet for part 2, look at the solubility chart on the back of the part 2, chapter 4 packet. You'll see this in the lower right-hand corner. That is a short list of metal activities. And so you see the way it's arranged here. The more active metals are on top, the less active metals are on the bottom. So every metal here is more active than the ones underneath it, okay? And more active means more easily oxidized, and less active means less easily oxidized. So we can use this chart to figure out if certain reactions will occur or not. Okay, let me show you how we do that. Ooh. So let's take a look at a different reaction. Suppose we have silver, Ag, plus zinc chloride. So here's my question. Will silver replace zinc? So in other words, will this happen here? That's right. The answer is no. And the reason is because silver is less active than zinc. How do I know that? I know it because I looked at the chart, and zinc is on top of silver. So it's more active. You could see that. So there will be no reaction. All right, here's another one. Suppose I have aluminum and copper nitrate. Will this happen? Will silver replace copper? Sorry, that's not silver, it's aluminum. So that's really confused the issue because aluminum is over here. Yeah, will aluminum replace copper? Yes, sorry about saying that wrong. And it will because aluminum is more active than silver. silver than copper. Okay, so what are the products here then? Single replacement. What is aluminum nitrate?
AL.
What is the charge on aluminum here?
Oh, +3.
Right, and NO3 nitrate,
That's negative, so you would need 3 of those.
right. And what's the other product?
Copper.
Copper, solid, with a 0 oxidation number. So here we had aluminum that was 0, right? No charge. What was the charge here? What about copper? What's its charge or oxidation number? +2. I don't care about nitrate. Nitrate's the same on both sides. So what happened was aluminum went from 0 to +3. So Al is oxidized. Okay, its oxidation number went up, or charge went up. And copper started as copper 2+. It goes from 2+ to 0. So the oxidation number or charge went down. So copper 2+ is reduced. And here's something students do all the time that's really wrong. Students will tell me copper Cu was reduced. Well, you don't even have Cu on the left side. You have Cu2+. It's the ion that got reduced. You didn't have Cu on the left side. So you really need to say copper ion is reduced. Okay.
So does it matter that one has 3? So,
Well, all right. Yes, it does matter. And this equation isn't balanced. But in terms of what's happening to an individual aluminum, it's going from 0 to +3. Yeah, I would have to balance this equation. So yeah, that's very true. I would have to put 3 here and 2 here and 2 here and 3 here. Yeah, then it would work out. Okay.
We need to always.
No, well, it depends on what you're asked to do. So will this reaction occur? And the answer is yes. Aluminum is more active than copper. Aluminum replaces copper.
So if there's no. Right side.
Right. If there's no reaction, then lots of times I'll ask you to write the products of these reactions. And if there is no reaction, write NR. No reaction. Yeah. Okay. All right. So far we've seen that one kind of replacement reaction. There's another kind of replacement reaction that we talk about in this course, and that is metal plus acid. So that's another type of reaction. And here's an example. Aluminum plus hydrochloric acid. What type of acid is HCl? Is it strong or weak? It's strong. You need to know the 6 strong acids. You need to memorize them. And you need to know HC2, H3O2, or HOAC. What is that acid? Yes, which you'll be working with in lab today, I believe. You need to know that, okay? So anyway, we have aluminum plus HCl. Yeah. Plus HCl aqueous. Oops. Goes to, okay. Now, aluminum replaces the hydrogen. This is sometimes called hydrogen replacement. Metal+Acid or hydrogen replacement, but I don't use that term though. And so on the left, we have this neutral aluminum metal. On the right, we have aluminum ions. Okay, so what happened was aluminum is oxidized to Al3+. So the metal is oxidized. Okay, and let's write the oxidation numbers. When you write an oxidation number, it's just for one atom. So oxidation number here is 0. Here it's +3. Okay, so you could see it's oxidized. The oxidation number goes from 0 to +3. But we know something has to be reduced when something is oxidized. Okay, so and I also haven't given you all the products here. The other product is H2 gas. Okay, so look on the left. Now, when you put HCl in water, this is aqueous, right? So it's in water. In water, what is this hydrogen? What is the charge on this hydrogen when you put this in water? It dissociates, remember, right? So you have H+ and Cl-. So this hydrogen here has a +1 charge because of the hydrogen ion here. So hydrogen goes from a +1 charge on the left, and now here, in the form of H2, it's part of the elemental hydrogen. That's 2 neutral hydrogen atoms that are bonded together. Whenever you have the elemental form of the natural form of an element, it's 0. Okay, so hydrogen goes from +1 to 0. Okay, of course it's not balanced. I have to put a 2 here. Actually, I have to do a few other things. That's not even balanced. I'm not even going to bother balancing it right now. But hydrogen, H+ anyway, is reduced. It goes from H+ to H2. Its oxidation number has gone from +1 to 0. Okay, so so I've gotten those. Now, what about the Cl? Here, the Cl is Cl-. I don't know how that got erased, but and over here, the Cl is Cl-. So the Cl- is not changed. We say it's a spectator ion. Let's see. I think to balance this, I'd have to have a 6, a 2, a 2, and a 3. Okay. All right, so that's the other kind of acid reaction. Acid plus a metal plus acid, I should say, but not every metal will replace hydrogen. It depends on how active it is. Yeah. I'm sorry, what did you say? It's H2 over here, yeah. Well, to tell you the truth, it's because that's what happens in a metal plus acid reaction. You get the metal plus the acid, and it gives you a salt plus hydrogen gas. It's always that way.
I think she's asking, how is there only one hydrogen on the left side?
I don't know what you're talking about. 3 times 2 is 6. 6 times. You have to balance it. That's the problem. I did balance it rather late, so probably was after you raised your hand that I balanced. All right. But anyway, this is what happens in that type of reaction. And you'll see these in lab next week because you'll be doing chemical reactions. So here's another example. Zinc plus HCl. And so zinc replaces hydrogen. And it gives you zinc chloride and H2. Okay, so this one does happen. But this reaction does not. Does not. So copper does not replace the hydrogen in HCl. Okay, so you might say, okay, well, let's look at our metal activity chart. Grab it again. Okay, so you could see here, let's take a look. We had zinc reacted with the HCl. That's right here. This reacts with HCl. Does not react. Oh, I forgot to do the handout of the day. Damn it. Oh. All right, let's go back to the previous reaction. Here's your handout of the day, number 1. So this is back. Forgot to do it. So this is asking, will zinc replace magnesium? Okay, so you can look at what we did here and answer that question. The explanation can be very short, really. There's a wrong date on top, but hello.
You said a less reactive not replace a more reactive.
That's right. It has to be a more reactive replacing a less reactive. A more active replaces less active. Oh, that's not what I wanted you to look at. Oh, I put it in the wrong place. I don't believe it. Ugh. Not yet. Yeah. Okay. Anyone got a question about this? Everyone done it with this? All right, let's go on to where I was. Okay. So zinc reacts with HCl, Copper does not react with HCl. This is basically, or any strong acid. Okay, so here's a question. Will silver react with HCl? So what's the answer to that question, do you think, from this information that you're given here? Why? So she says no. So the reason why?
Copper can't react with strong
Right. If copper can't react with strong acid, and silver is less active than copper, then silver can't react with strong acid. So basically, anything down here will not react with HCl or any other strong acid. And all these guys up here will react with HCl. Okay. So I just want to give you a little more terminology here. Here was that acid plus salt reaction that we looked at. And we already determined that zinc gets oxidized. And the copper, which is +2, gets reduced. So here's another little bit of terminology. The chemical that gets oxidized is responsible for causing the other chemical to get reduced. So the thing that gets oxidized, we call the reducing agent. The thing that gets reduced causes the other thing to get oxidized, so we call it the oxidizing agent. Okay, so it's always that way. So if you look at this reaction that we just talked about, HCl goes to zinc chloride plus H2. Okay, what's oxidized here? And what's reduced? This is oxidized. It goes from 0 to +2. The H plus in HCl gets reduced. So that makes the thing that gets oxidized is the reducing agent, and the thing that gets reduced is the oxidizing agent. Okay. So now I'd like you to take out the next activity sheet, okay, which has some practice with this. I think on yours, it says to write the net ionic equations. We're not doing that this year. You can just cross that out. Okay, so magnesium and sulfuric acid. So let's just, I'll work on this first one with you. That's Mg solid. What's sulfuric acid's formula? You have to memorize these. That's it. H2SO4. So what happens here? By the way, I repeated that information up here. When placed in HCl, zinc metal reacts, giving off hydrogen gas, while copper does not react. So we know that this will react with strong acid, and on the bottom, it will not react with strong acid. So you're given that information. I give you that information generally. So my question is, will this happen? Yes. And why will it happen? Because zinc reacts with strong acid, and magnesium is more active than zinc. So it will certainly react with sulfuric acid. And when it does, it will produce MgSO4 plus H2 gas. And I believe that that is already balanced. But it's a good idea for practice to put the charges here. 0 plus 2. So Mg is oxidized to Mg2 plus. Mg gets oxidized. So that means that Mg is the reducing agent. And this is +1 over here. Now notice, this is something we do all the time. Hydrogen is the hydrogen ion. When an acid breaks into ions, you get H plus here and SO4 2 minus. I put a +1 on the top. +1 is for one hydrogen. The numbers, the oxidation numbers are for one atom. Okay, so I know that there's 2 of them, and you might think I'd put a +2, but no, we analyze what happens to one atom. Okay, it goes from +1 here to 0 here. So H plus in H2SO4 is reduced to H2. The charge goes from +1 to 0. Here, the charge went from 0 to +2. And of course, since there's 2 of them, that's how the charge is balanced. But we're not balancing redox equations this year. That's not one of the things we're going to do. Okay, so I'm going to leave you to do the other 2. I'm going to walk around. And if you have questions, please ask me what your questions. Cold again. This room goes hot, cold. Temperature regulation is not so good. My scarf on. See, the numbers that we write on top of oxidation numbers, there's just one of one ion. That's how we analyze what atoms are. In order to balance,
Yes. Yeah. But, yeah, that's what. Right, half AO2, that's 3. I was confused about that. Technically, yeah.
Try to struggle to write products, there's no reaction. And or man. Nothing is oxidized. Yeah.
Maybe. Right. So it's AO.
This is. That's what it says. Propane. It's really great. How does that sound?
Yeah.
Let's take the side, it would gain. I mean, you know, you balance, right?
Gains 3.
That's gonna be what makes some of the fact that it looks like, you know. Yeah. Anybody down there have questions?
That's all you really need.
No.
You don't. Yeah.
Yeah.
Safety matters very
Yeah.
Oh, it doesn't.
So the only thing wrong here is.
Balance it.
Because
So that-
it's not zinc, because it isn't zinc. Divided by so put iron is. Okay, so basically everybody I saw realized that this is no reaction. Why is it no reaction? Can someone help me with that? Speak up, speak up.
Because the, platinum, it's less acid. That's the strong acid. They don't, it doesn't react with the strong acid on the bottom of that thing.
All right, let's because you're right, but let's put it more specifically, because the platinum is a less active metal than copper, and copper does not react with strong acid. And how do I know copper doesn't react with strong acid? Because it says it over here. Okay. So platinum, that's no reaction. Down here, first you have to ask yourself the question, is aluminum more active than zinc? Because if the answer is yes, then this reaction will occur. And the answer is yes. So this reaction does occur. The thing is, here, you have to get the compounds right. And you have to know that aluminum in an ion form, which is what happens when aluminum gets oxidized, is +3. So you have a compound with aluminum and sulfate, and that compound is this. Okay, so you have to know, and you will have your ion charts, right? You will have your you'll have your periodic table. Aluminum is a little hard, right? Because it's in that group 3. It's on the right side, but it's that one sort of metal there that's on top in group 3 that you have to know that means it's a +3 charge. So aluminum goes from 0 to +3. So aluminum is oxidized. And now what's reduced? Did you say what? Zinc? Did you say that? Okay, zinc is reduced, is not quite right. What do I have to, how do I modify this to make it right? Is it zinc on this side? Zinc +2 is reduced to zinc on the right side. Yes. Sorry, one question at a time. Oh, yeah. She got the gotcha, not you. Sorry. Sorry. All right, very good. This goes from +2, thank you, to 0. I was on autopilot, but. All right, I'll take that special problem from you. All right, so now I have to move on. I'm going to talk about another type of redox reaction, which is combustion. Okay, so we have 2 different kinds of combustion we talk about here. And the first type is combustion of a metal. So you take a metal plus oxygen to give a metal oxide. Okay, so for example, copper plus oxygen gives you CuO. There are other oxides it could make, but this is a good one. You would have to balance this. And this is solid copper, gaseous oxygen. Metal oxides are solids. Okay, they are also all ionic compounds. So what happened here is that copper that was 0 here was oxidized to copper 2+. And oxygen, now here we have 2 neutral O atoms bonded together. That's neutral, 0. And what is the charge on an oxygen and copper oxide here? -2. So copper is oxidized from 0 to +2. Oxygen is reduced from 0 to -2. Okay. Or you could write O2 is reduced. Either one is fine. Okay. So another thing is that metals react more readily with oxygen if they are more active. By the way, this reaction, you have to heat it up. And so heating in a flame is how this is normally done. Okay, you take a piece of copper, stick it in the flame, and you'll see that the copper turns black and that black stuff is the copper oxide. So another example here would be if you take magnesium plus oxygen, and you'd get MgO. And very similar to with copper, this goes from 0 to +2. So Mg is oxidized. The O2 is reduced. Here it's neutral. It goes to -2. So, okay, that makes oxygen the oxidizing agent. Oxygen is the OG oxidizing agent, the original oxidizing agent. That's where the word comes from, okay? Oxygen is the original oxidizing agent. Well, so the thing that's reduced is always oxidized. The thing that's oxidized is a reducing agent. It is the agent of the oxidation of magnesium. What? No. And something that is oxidized is the reducing agent. Something that, no, it can't be both. Although there are disproportionation reactions where it can be both, but not today. It's not, yeah. Okay, so what I wanted to say though, remember I said metals react more readily with oxygen if they are more active. So if you compare this reaction, the magnesium oxidation to the copper oxidation, the magnesium oxidation is really dramatic. It's like a bright flame, and it, you know, you can't even look at it. It's so bright. It gives off all this UV light. So the magnesium oxidation is way more enthusiastic than the copper. Copper just turns a dull black. Magnesium, it's like, phew, bursts into flame, and it disintegrates into ash, basically, which is magnesium oxide. So the reaction of Mg with O2 is much more enthusiastic. And that's because magnesium is more active than copper. Okay? Now, I want to get into a different kind of oxidation, a different kind of combustion reaction. So this kind is combustion of a carbon, hydrogen, or oxygen compound. So contain any of these, C and H or C and H and O. So I'll give you this example here. Here's CH4O. This is actually methanol. And it reacts with O2. It's a liquid. And does anyone know the products of this reaction? Because we've looked at reactions that are similar to this. What are the products of a combustion reaction when you start with a carbon, hydrogen, or a carbon, hydrogen, oxygen compound? Yes, that's right. Water and carbon dioxide. And if you balance this, you get 2 and 4. There we go. That's the balanced combustion. So now we have to ask ourselves, what is oxidized here and what is reduced? And it is really not obvious what is oxidized and what is reduced. And why is that? Why is it so it's not obvious? The reason is because these are not ionic compounds. So we don't have ions with obvious charges. Okay, we have all, these are molecular compounds, every one of them. What do you think is oxidized here? Remember, I told you that O2 is the original oxidizing agent. Right? So so that means that this thing must get oxidized. This is oxidized because I know this is the oxidizing agent, and the oxidizing agent gets reduced. But that's not good enough to give me, what is actually getting oxidized in this reaction. So it's very difficult to figure out from what we know so far, what gets oxidized and what gets reduced. And that is why chemists have come up with a set of oxidation number rules And what these rules do is they assign these different numbers to all of the players, all the elements within compounds, all the atoms within compounds in chemical reactions. So these assign oxidation number values to every element in a compound in a reaction. Okay. Also assigns them to ions, but the charges on ions, they're obvious, so that's not anything new. And the reason why this is somewhat difficult is because in molecular compounds, so this is most important for molecular compounds, and the reason why it's difficult and not obvious is because molecular compounds share electrons. So it's not as clear which atom has the electrons, how they're shared in there. So they share electrons, but the sharing is not equal. I'll give you an example, very big, important example, water. In water, oxygen kind of grabs more of the electron density. So oxygen ends up with a slight negative charge. We call it delta negative and delta positive. Delta means small. Okay. So in water, the oxygen is more negatively charged really than the hydrogens are. So the oxidation number system tries to sort of sort this out and assigns numbers to every element in a compound. And the motivation for this is to see where the electrons are going. in a chemical reaction. Okay, so the oxidation number system sort of sorts this out. And you can see where the electrons are going. But it is wrong to think of the charges in a molecular compound, the oxidation numbers, it's wrong to think of them as full charges. They're really hypothetical values, and they just give you an idea of where the electrons are going. But yeah, I know it's a little bit touchy-feely, you know, it's not exact, but that's the way it is. So let's go through these rules. Some of these you already know. The oxidation number of a pure neutral element is always 0. So we've seen this. We've seen it in H2. If you have an element iron, just irons, which will be solid iron, right? But even if it was liquid iron, it would still be 0 because it is a pure element. Okay? Carbon by itself, pure element. If you have a monatomic ion, what that means is that you just have one thing, like Na plus or Mg2+. The oxidation number is equal to the charge on the ion. Okay, here the oxidation numbers are all 0. Okay, we know that the oxidation number of the fluoride ion then would be -1. So I could have F minus, the oxidation number is -1. But fluorine in any compound is assigned the oxidation number of -1 in all of its compounds, except, of course, if it's F2, because that's the neutral element, and that would have an oxidation number of 0. Okay, if we have oxygen in a compound, it's always going to have an oxidation number of -2, except in these compounds that we don't cover, so don't even worry about them. If you have a group 1A metal and hydrogen, the charge oxidation number is +1. There's an exception that we don't talk about, we don't cover. In group 2 or 2A, the oxidation number is +2. These are the very important ones down here. These are more important, okay? Because this is what allows you to figure out the oxidation number of elements in a compound. You should have this. You shouldn't need to squint at the at the board. Anyway, the sum, so if you have a neutral compound, the sum of all the oxidation numbers of all the atoms has to equal 0, because that's the charge. It's charge of 0. It's a neutral compound. I'm going to show you how to do this. For a polyatomic ion, for example, in phosphate, okay, the sum of all the oxidation numbers of all the atoms equals the charge on the ion. So for the case of phosphate, it would be -3. This sounds a lot harder than it is in practice. So let me show you. Let me go back to that reaction. CH4O plus O2 goes to CO2 plus water. Okay, and now I'm going to focus on one of these compounds at a time. Let's focus on CH4O. Okay, so we're going to use the rule that the sum of all the oxidation numbers of all the atoms in this compound is 0. But we know some things. If you go back to the rules, What is the oxidation number of hydrogen in any compound besides H2? Go, where is it? The oxidation number of group 1A metals and hydrogen is +1. So I know that this hydrogen here, notice I'm going to write +1, not +4. Okay, because that oxidation number is for one hydrogen atom. Okay. What's the number I assign to oxygen here based on the rules that you have in front of you? -2. And carbon is the one I don't know. So in math, when you learn about algebra, what do you call the thing that you don't know? Right, and what do you assign it as? Let X, okay, that's going to be X. So now I have to add up all the oxidation numbers, and it's going to equal, the sum is going to equal 0. So what is it? So I have X plus 4 times +1 for the 4 hydrogens, plus 1 times -2 equals 0. So that's X plus 4 minus 2 equals 0. X, what's 4 minus 2? Plus 2 equals 0. X equals -2. So that means that the oxidation number of the carbon is -2. So I have CH4O, -2 plus 1, -2. Okay. And notice if you add up 1 times -2 plus 4 times +1 plus -2, that's -2 plus 4 minus 2, that sums to 0, which is how we got that -2 for carbon. Okay. So we figured out that the carbon's oxidation number here is -2. Now, the reason I'm writing these down is because to figure out what gets oxidized, what am I looking for? What's going to happen to the oxidation number? It's what? How is it going to change? What? Is it going to go up or down? No, oxidation, because it's going to go up. Reduction is when it goes down. Okay. All right. So what's the oxidation number of oxygen in O2? 0. Okay, now we have carbon dioxide. So let's do CO2. Okay. So C is going to be the X. Oxygen is -2. So what's this equation going to be? X plus what? What? Let's just do 2 times -2, right? You have 2, and they're -2 each. And what does that sum to? 0. So it's X minus 4 equals 0. So X is plus 4. So this X is plus 4. So I'm going to go back to my equation now, and I'm going to write in the plus 4 over here. What's the oxidation number of the O in this compound? And it's for one oxygen atom. Guess again. -2. It's always -2, unless it's in O2 when it's 0.
On the product side,
It's not that it's on the product side. It's that it's paired with, it's that it's always -2 in compounds, except O2. Look at the oxidation number rules. Yeah.
Oh, yes, it's the natural.
Right. Well, but no, the natural form in O2 would be 0. But O2 is 0 on this side. On the other side here, it's in a compound, so it's -2. All right, what about over here? What's the oxidation number of oxygen here? -2. What's the oxidation number of hydrogen? +1. Okay, in compounds, except for H2 and O2. H2 is 0, O2 is 0. In any other compound with hydrogen and oxygen, except for these peroxides that we don't study, hydrogen is +1, except in hydrides, which you don't study. Hydrogen is +1, oxygen is -2. So whenever you see it, right, you'll know it. So now what you have to do is examine the numbers, okay? And you have to tell me what number went up and what number went down. So that means carbon in CH4O is oxidized. Okay. What else? O went from 0 to -2. Here's 0 here and -2 here. Okay, so that means that O in O2 is reduced. Or you could just say O2 is reduced. The hydrogens, you'll notice, are +1. It doesn't change. But the carbon changed and the oxygen changed. Yeah, this is not a 0 there. Why did I do that? That's a -2 there. Duh. I just didn't copy it right. Okay. So what you could see here is that the carbon is oxidized. So this thing is oxidized. It's in particular, it's the carbon in CH4O that is oxidized, and the oxygen is reduced, which, by the way, makes oxygen the oxidizing agent, which is why it's called oxidizing. It's why it's called an oxidizing agent, because oxygen so often is the oxidizing agent in many reactions. Okay. This is just going to take practice. That's all. That's the way it is with chemistry. You got to work a lot of time outside the class. I know. So let's take a look at the activity here. Okay. Find the oxidation number of each atom in the following formulas. Now you have to start with what you know from the oxidation number rules. Okay, so what you know is that oxygen in compounds is -2, unless it's O2. Hydrogen is +1 in compounds, unless it's H2. What about potassium? What does it say in the oxidation number rules? Potassium is a group 1A metal. What is its oxidation number? +1. What is oxygen here? -2, right? So I have this Mn is going to be the X. So I have X +1 plus 4 -2s equals 0. So the oxidation number of the manganese is +7. Right now I have nitrate. I'll let you digest that one another. I have to tell you that I'm not going to have time to go through all of these. And so it's going to be your responsibility to go through these and go through the answers. Because what I have down here is a whole bunch of reactions. Okay. we're not gonna probably get to the HOD. I don't know how we could, but to figure out what's oxidized and what's reduced in these equations, you have to go through and assign oxidation numbers. All right, let's see how far we can get. I'll do a few of these. Are there any questions about this? NO3 minus, NO3 minus. Yeah, the sum of the oxidation numbers here will be -1. Because that's the charge on this ion. Now, what is the oxidation number of the O? -2. The N is the X. So what's the equation going to be here? X equals -1. X minus 6 equals -1. All right, I'm going to leave this for now. I think we got the hang of that, I hope. And I want to say that in this part, you have to decide which of these reactions is a redox reaction. Okay, they're not all redox reactions. But the way to figure that out for sure is to look for oxidation numbers. And I say that you should use your knowledge of reactions. For example, if you see a nitrate here and a nitrate here, then there's no reason to figure out the oxidation numbers within that nitrate because it doesn't change. It's NO3 minus on the left and NO3 minus on the right. So let's do this one. This reaction, copper, what's copper's oxidation number here? Yeah, it's neutral. What is it here? This is an ion, so it's easy to know the oxidation number. We've been studying this since chapter 2, right? So what's the charge on the copper? +2. So you could see that copper is oxidized here. What's the charge on the silver here? +1. And what's the charge on this? 0. So you could see here, this is redox. The copper is oxidized. The Ag plus is reduced. That's not the example I wanted. Here's an example that I want. HBr, what's the charge on the H? This is a strong acid. So what is the charge here? What happens when you put a strong acid in solution in water? And what would the charge be on the H? +1. Bromine, -1. What's the charge on the calcium here? Second group of the periodic table. And now, what's the charge on this oxygen? Given the oxidation number rules. Remember, this is part of a polyatomic ion, but we already know that O is -2 and H is +1 because those are the oxidation number rules. Okay, so that doesn't change here. And the calcium is +2 and the bromine is -1 here. So is this a redox reaction? H +1, H +1. Bromine -1. Bromine -1. No, I thought you were telling me bromine wasn't -1. So this is not redox. Nothing changes about the oxidation numbers. Okay. What about this famous reaction? What's the hydrogen here? Oxygen and H2O, H. Oxygen. Yeah. Now, I really don't want you going around after class and telling your friends that the charge on hydrogen and water is +1 and the charge on oxygen is -2. These are not really charges. They're hypothetical numbers we call oxidation numbers. H2O is a molecular compound where electrons are shared. What that's simply indicating is an unequal sharing where oxygen is more electron grabby than the hydrogens. But these aren't really full charges, but anyway, whatever. Yeah, don't tell your friends that. Thank you. The numbers on that the oxidation numbers are for one atom. Yeah, always.
So if they don't. So was oxygen was reduced on that one?
Oh, let's finish this. Yes. And that's right, because oxygen is the original oxidizing agent. So this is reduced. This is oxidized. So this is the reducing agent and the oxidizing agent. So if you're like on an exam or something and you see a reaction with O2, you know, it's probably the case that oxygen is oxidizing the other thing, because that's why it's called oxidation. It's the original oxidizing agent, which means that the oxygen would be reduced, but that's not true in every single case. So you might get into a little trouble with that. Time is it? All right, I got a few more minutes. Here, I think, so this was a handout of the day that we didn't get to. So you should make sure you do these, because you're going to hand in the HOD with what you have so far. Just the first one is fine. But you should do the rest of these, and I have the solutions that will be posted. Okay, but I don't have any more time to give to this in class. Let's just do one more of these, okay? Let's do this one. And then this one, actually. Let's do both of these. I think we have time. So you want to work on the oxidation number? What would be the oxidation number of hydrogen here? +1. So this is going to be our X. So now we have a 2 here to contend with. 2X plus 6 times +1 equals 0. 2X plus 6 equals 0. 2X equals -6. X equals -3. So that means that -3 is the oxidation number of the carbon. ClO4 minus. This is the other ion that you get from the strong acid HClO4 when it breaks up in solution. The oxygen we know has an oxidation number of -2. The chlorine we don't. So here we have X plus 4 times -2 equals what here? What do I put here? -1. X minus 8 equals -1. Add 8 to both sides. Okay. Okay, I didn't have any time to go over limiting reactants. So you have to study limiting reactants. Somebody told me that, what's his name, Tyler, who? Does he have a good, Tyler DeWitt has a good thing on limiting reactants. Because you're gonna see it on the quiz on Thursday. Okay, have a good lab.
From the problem.
Yeah.
So. Number 4, number 5. I get.
Size and brand.
For the, because the charge on the ion is negative. Oh, yeah, so for a poly, it's how much ion the oxidation sums the charge on. Okay, thank you. Okay, mine, I have the actual. And this computer is hot, it is hot. Yeah.
Yeah.
Well, you might as well, I'm probably just gonna sit with you here. Is there another chair? No. Maybe I'll sit over there with you. I don't know. What am I looking for here?
It was number 5 and 8 was